Okay. And then up next, two short variants, only briefly, to other applications or methods, algorithms that uses bottom-up subspace search. The first one here is so-called FIRES method. It uses, again, bottom-up heuristic for subspace search, using or starting with one-dimensional clusters. They call it base clusters here. And they can be generated by applying any arbitrary clustering algorithm of your choice to each of the one-dimensional subspaces. So you take all one-dimensional features by themselves and apply, for example, k-means. Yeah? So if you have d features, you apply d times k-means, or d times dbscan, or whatever you want. Yeah? So those one-dimensional clusters are called base clusters. And the second step, you merge those base clusters and generate subspace cluster approximations. And how do you do that? Well, you apply a clustering of the base clusters. Sounds a little weird, but okay, it's a variant of dbscan, and you use a different notion of similarity. Now you want to cluster base clusters, yeah, and the similarity between base clusters is defined by the Schnittmenge, the intersection of the two base clusters. So the more points two base clusters share, the more similar they are, and the higher the likelihood that they are in the same cluster. Yeah? And we apply dbscan using this, or the authors apply dbscan using this similarity in order to generate maximal dimensional subspace approximations, actually. Yeah. So here you see you have some base clusters, and for example CB here and CA here, they share a lot of points, so they may be packed together to these to some subspace cluster approximation, which is actually this rectangle here. Yeah, and the same holds true with CC here, and CA also share a lot of points, so they may also be a second cluster detected by dbscan here in this second step. Yeah? So and yeah, as you see here, I mean the approximation is quite coarse, so there may be some points that in this rectangular approximation that is not exactly a member of the cluster, or the rectangular approximation is too small, so there may be some points outside which should belong to that. So the authors suggest to refine the resulting cluster approximations using any traditional clustering algorithm, yeah, on the points within the approximations. Okay, so for example, getting rid of those here. Those guys here. But the most important point is start with one-dimensional clusters, base clusters generated by anything, what you want, and then you apply dbscan with a similarity measure, measuring the intersection of the two base clusters. How many points in the two base clusters have in common. You know? And there is a variant which is very similar. The idea is very similar. It's called P3C. Here the cluster cores are hyperrectangular approximations, again, of subspace clusters. And the subspace search is now not a dbscan run, which is quite efficient here. So here it's again an a priori style. So cluster cores are computed bottom up from so-called significant one-dimensional intervals. Yeah? And the new thing here is, so actually this is more or less clique, yeah. So you have one-dimensional intervals that are significant or dense, and then you apply a priori to get higher dimensional rectangular subspace clusters or grids, yeah, grid cells. But so it's more or less a variant of clique with a different cluster model, because now intervals are called significant by or the significance of one-dimensional intervals is determined by using a hypothesis test from statistics. Yeah, so the hypothesis is that in the whole thing there are no clusters, meaning the points are randomly distributed, and then you can compute the probability how many points should be in one of those intervals. Yeah? And if an interval contains significantly more points than expected, the hypothesis is rejected by some significant level, significant value, yeah, alpha typically. Yeah, so it applies a hypothesis test here, and then the rest is more or less the same like clique. Significant one-dimensional intervals follow the downward closure property. That's nice. So you can apply more or less the same like clique. And then the authors also propose a post-processing where those cluster cores initialize an EM, fuzzy clustering, of the data points. Yeah. So I think the authors of this paper here, P3C, maybe just thought that this one here is not enough for a significant new contribution, so they came up with the idea of post-processing the whole thing with EM, which is a nice idea anyway, because EM somehow can accommodate those subspace clusters actually. Yeah. Okay, so another variant from the bottom-up phalanx of approaches is DISH, which is the idea of finding subspace cluster hierarchies. So hierarchies meaning in that case that you have these redundancies where you have lower dimensional clusters embedded in higher dimensional ones. Yeah. So for example here you have a one-dimensional cluster C here, which is embedded in this plane here, which is the blue one here, which is B. Yeah. So C is embedded in B, but it's also embedded in this plane here. So the C is a line, and the line may be embedded in several planes. In this case, it's embedded in the plane B and in the plane A. So C is in the hierarchy a sibling of those two here. And D, the line D here, is embedded in this one here. So D is a sibling of B here. Yeah, and DISH actually integrates a proper distance function into hierarchical clustering, namely optics in that case, and it learns distance-based function, distance function on an instance level and bottom up again. Yeah. We don't go into much detail, just that you know, if you are interested in those subspace cluster hierarchies, then you can apply a different method, or there are some methods that can search for that. Yeah, so this just should give you another idea of how you can somehow play with the concepts of subspace clusters, and especially with those redundancies or relationships between lower dimensional projections and higher dimensional projections. Yeah? That might be an interesting information for you. Yeah, some summary on subspace clustering. Well, we have several different variants here. Most of them have the key limitation, which is global density thresholds. I mean, we talked about that before. It is typically applied in order to assure or ensure the downward closure property, which is just a performance thing. Yeah, it's not an accuracy thing. Yeah, so the density threshold must be fixed globally, meaning that points in, for example, a 20-dimensional subspace cluster must be as dense or as similar or as small a distance as in a two-dimensional cluster, which is quite a hard claim. Recall that hypothesis space grows, distance space grows, and so on and so on. So all what we know about the recursive dimensionality is somehow a contradiction to this assumption of a globally fixed density threshold. But anyway, that's how it is. So this is a rather optimistic assumption. Yeah, we had that before. Consequences, we also talked about that before. A very strict threshold will most likely produce only low-dimensional clusters, but in a shorter time. A loose threshold will most likely produce higher dimensional clusters, but also a huge amount of lower dimensional clusters that are potentially meaningless because they are completely redundant. Yeah? And the runtime will also increase heavily in that case. Yeah? So you see this threshold here now is a trade-off between scalability or runtime and more or less the amount of insights you get from the results. Okay,